All right, so let's go ahead and work on a practice example here. Here we have four different structures. We've called them A, B, C, and D. And we're going to do a handful of things. First, I guess it's listed last, but we'll do it first. We're going to talk about the intermolecular forces present. That's just going to be a review from stuff that we talked about previously. And then what we're going to do is we're going to identify what is the most acidic proton, and then we're going to rank them from 1, 2, 3, and 4 in terms of most acidic to least acidic. And we're going to be using the trends that we talked about in the last video about thinking about the stability of the conjugate base to kind of justify which of them is going to be more stable versus less stable, and therefore more acidic and less acidic. So let's go and start by just thinking about our intermolecular forces, or our IMFs, just as a little bit of review. Don't want you to forget about them. If I look at A, it exists, so it has London dispersion forces. And actually, I'm just going to go ahead and cheat, and I'm just going to give London dispersion forces to all of them because they exist. They have bonds, and if you have bonds, you have the ability to form these temporary little dipoles that come about from our LDFs. Let's then think about our dipole-dipole and our hydrogen bonding. In A, I don't have any OHs, NH2s, NHs, so I don't have any hydrogen bonding. And I don't actually even have anything electronegative. It's all just carbons and hydrogens, so I don't even have a dipole. So in A, I only have my London dispersion forces. If I look over at B, I will have a dipole because I have some electronegative stuff. I have some oxygens, and the right side of it has more oxygen, so there's going to be a dipole pulling over to that. So we have dipole-dipole, and I have an OH, specifically a H connected to an oxygen. That's going to make that field especially positive, so that means we're going to have some hydrogen bonding. So in B, I have all the intermolecular forces. If I look at C, I have an oxygen, which is going to be more electronegative. That's going to give me some dipole-dipole. And I also have an OH, meaning I have the ability to hydrogen bond. And then finally in D, I will have London dispersion forces, and I will also have some dipole-dipole. Because of the fact that I have fluorines, those fluorines are more electronegative, so there will be a dipole towards those fluorines. So those are kind of all my intermolecular forces for each of those different structures. And that's just kind of a quick little tidbit of review and kind of practice from stuff that we previously talked about. Now let's go ahead and try to figure out what is going to be our most acidic H. What would we abstract as a proton? So let's go and start with A. For A, the first thing I want to look at is, do I have any non-carbon stuff? And I don't. So that means I'm going to have to choose one of the hydrogens that are going to be on my carbons. And for that, I'm now going to think a little bit more about my hybridization. And here, I'm going to want to get something that's going to be on my sp hybridized. So this hydrogen here, and I'll go and maybe highlight it in yellow, is going to be our most acidic. That's going to be better than the hydrogens over here. There's going to be 3 at the end of this methyl here. Those are sp3 hybridized, where my other one's going to be on our sp hybridized carbon, and that's going to help stabilize better. So here, the one on the right-hand side is going to be better. Now, if we look over at B, I have some oxygens, and they carry some hydrogens. So I'm going to focus on those. Anytime I see a hydrogen that's connected to an oxygen or a nitrogen, either just anything that's not carbon, that's going to be what draws my eye, because that's going to be able to be more stable because it's more electronegative. So that gives me 2 possibilities, this one over here and this one over here. Both of those are going to go to oxygen, so they're going to tie in terms of your relative strength. However, on my right side, I have a carboxylic acid, where on my left, I just have a alcohol. And because of that, my one on my right side is actually going to be more acidic, because of the fact that I can get resonance with the carboxylic acid, where a charge on the other oxygen on the left would be stuck there. It would be localized. I could not do any resonance. So ultimately, I'm going to choose the one on my right being my most acidic. If I look over at C, I see that I have an OH, and anytime I have a hydrogen that's connected to something that's like an oxygen or a nitrogen, I'm going to focus on that before the carbon. So I'm going to hop in immediately over at number C, or sorry, I'm going to hop over at the OH, H on my C. And then for D, there's actually only a single proton, or sorry, a single hydrogen that we could abstract as a proton all the way down there. So those 4 different hydrogens that we've all highlighted would be the 4 that would be the most acidic that could be removed as a proton. Now in each of these, let's now consider what would be the conjugate base. And the conjugate base would be what would be formed if it is an acid. So if we had a base and that base came and abstracted that proton and then gave us a lone pair on the atom that that H is connected to, that would be the kind of overall reaction. And we want to show the product, which would just be the deprotonated version. So yeah, I can keep it on the same page. In A, I would have a triple bond that would now have a lone pair at the end and carry a negative charge. In B, I'm going to have everything be mostly the same, except instead of an OH at the right side of my carboxylic acid, I'm now going to have an O-. In C, I'm going to deprotonate the alcohol to get an O-. And then in F, we'll have our fluorine, 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 and then our triple bond, which will also be deprotonated and a negative. And each of these would be considered our conjugate base. These conjugate bases simply had that proton removed and then got a lone pair on the carbon that that H was originally attached to. Now, when we're thinking about the relative strengths of these, we are going to be using these to kind of compare and contrast our kind of rules that we talked about in our last video. Thinking about things like resonance and inductive effect and things of that sort in order to rank them in terms of stability. So for each of these, let's go ahead and kind of start our general, and we're going to rank these from most acidic to least acidic. The first thing that I see is in B and C versus A and D. B and C are both connected to an oxygen. And we know that oxygen prefers a minus charge over carbon because of electronegativity. So my number 1 and 2 spot should be B or C, and my number 3 and 4 spot should be A or D. Even if A and D have some resonance or they have some inductive effects, that's not going to override the kind of impact of kind of like being on our oxygen. You could also use your relative pKa's to kind of like get that relative pairing there, but that oxygen is definitely going to win out our carbon. So that's immediately going to tell me B and C are going to be 1 and 2, and A and D are going to be 3 and 4. I just need to figure out which is which in each of those pairs. And for that, then I'm going to use my kind of rules about like resonance and inductive effect. So let's go ahead and start by comparing B and C. So let's do B versus C. In B, I have the ability to do resonance because of that carboxylic acid. I can have this come in here and then resonate up, where in C it's stuck or localized just on that oxygen. So here, resonance in B makes it more stable than C, and that's going to make it overall a stronger acid. So at this point, I can now pretty confidently say that B is going to be ranked first for our most acidic, and then C is going to be second. And that difference between those two is the fact that B is able to do resonance where C cannot. You could also argue that this OH is electronegative, so it actually does have some inductive effect as well. So B actually does have some inductive effect and resonance where C has nothing. So that's kind of a little bit over the top, but does also help stabilize it even more. Then if I look at A versus D, as in my kind of trying to figure out third versus fourth, here I see they're very similar in structure. They're both going to be a lone pair on our alkyne, But I see that D has those fluorines, and those fluorines are electronegative. So these are going to help stabilize D through the inductive effect. So in my A versus D, we're going to have inductive effect from our fluorines in D. And that is going to help stabilize our conjugate base. So because of the fact that D has some ability to have inductive effect, I'm going to give this a ranking of third, and then A my ranking of fourth. I'll zoom out to maybe try to capture all of that in just one image. So in terms of my relative comparisons here, the very first thing I'm doing is I'm looking at my what is actually holding that charge. Oxygen is going to win out over my carbons, so that gives me B and C in one camp and A and D in a different. B has the ability to do resonance, so it's going to win out over C. And then D has some inductive effect, so it's going to win out over A. And that's where we can kind of use those kind of general trends from our last video rather than blindly memorizing some pKa's. If you wanted to kind of go based on purely pKa, in B, we know that pKa of a carboxylic acid is around 5. C, pKa of an alcohol is in that 15 to 16 range. And then the pKa of our alkyne is going to be around like 25. So we know that B is going to beat C, and that's going to beat A and D. So you kind of have that relative ranking based on pKa. But the benefit here is we don't need to know pKa's. We can just use our kind of like relative trends and things, so we don't have to memorize. And that's why we're kind of like doing this rather than memorizing, because save that brain space for something else. So we'll go and end there, and then we'll get some more practice next time.